Welcome again to Last Minute Physics. I'm Matt Montrief and this is Chapter 17. As always, here's the equations you're going to need to know for this chapter. First, n equals c over v, where n stands for the index of refraction, c stands for the speed of light, and v stands for the apparent velocity. I'll go into detail later in this video. Next is Snell's law, which says n1 sine of theta 1 equals n2 sine of theta 2. Again, I'll explain later. Okay, the first topic in this chapter is reflection. Reflection is a fairly easy concept and there's not a lot of work involved. So first we need to understand the two kinds of reflection, regular and dispersion. In regular reflection, the angle of incidence equals the angle of reflection, which simply put means that light bounces off at the same angle that it hit with. Again, this is called regular reflection, and all it means is that theta of incidence equals theta of reflection. The next kind of reflection is called dispersion. Basically, when light hits a surface such as paper, where it's not as smooth as a mirror and it's pretty rough, it bounces off in all different directions. There's no set angle that it will bounce off at. Now, on the surface, paper might look very flat and smooth, but at the microscopic level, it's very rough. Again, this is called dispersion. Refraction is probably the biggest topic in this chapter. Basically, the idea is, if we have a block of glass or some substance, we're asking what happens to light as it enters the different mediums. Here's how to draw these diagrams. So let's say we have a block of glass, and this is the air. And here's the beam of light being shot into the glass. We always draw the normal parallel to the surface. For those of you who don't know, all the normal is basically just a reference point to measure angles from. We always measure angles from the normal. Okay, now normally light wants to travel in a straight line, so I'm just going to draw that in here as a dashed line. Now what happens to light as it enters the glass is that it slows down, causing it to get bent toward the normal. We call this angle the angle of incidence, and this angle the angle of refraction. Notice that both of them are measured from the normal. To completely understand this, we have to understand why light slows down when it enters a medium. Well, technically it doesn't actually slow down, it just seems like it does. So let me explain. Air is a gas and therefore not very dense, and it's easy for light to travel through air without bumping into any molecules. But when it enters a solid, the molecules are tightly packed together and the light bounces off them like in this diagram. Notice that the light must travel a greater distance and therefore it takes more time, making it appear that the light is going slower. The speed of light is still constant, but the apparent velocity, represented by the letter v, will always be less than c. We're going to be using Snell's law for pretty much all refraction problems, so it wouldn't be a bad idea to memorize it. It's just n1 sine of theta 1 equals n2 sine of theta 2, where n stands for the index of refraction. This just tells us how dense the substance is. We base all densities off of a vacuum, which has an index of refraction of 1. Some common examples are air, which is also 1, water, which is 1.33, and glass, which is 1.5. Theta, as you probably already know, is the angle at which the light is measured from the normal. Notice that in the equation that there is an n1 and an n2, also a theta 1 and 2, which means that the n value for one substance will not be the same as the other substance. This is also the case with theta 1 and 2. Page 353 in your book will show you all the index of refraction values at the top in the table. So let's draw out a simple refraction problem. The easiest way to set these up and to stay consistent is to put all information from one side of the boundary on one side of the equation. It doesn't matter which side, just make sure you stay consistent. So for this problem, I'm going to put all the top information on the left and all the bottom information on the right. If this confuses you, just either hang in there or just forget I said anything. So let's draw our normal and say that this beam of light is contacting this boundary at angle theta. So normally, like I said, light wants to travel in a straight line, but we know it's going to be bent towards the normal, causing this angle theta to be the angle of refraction. So let's say the top is air and the bottom is water, and then n would be 1 for air and 1.33 for water. So to set this up, we're just going to use Snell's law. And like I said earlier, everything from the top is going to be on the left. So the top n is going to be 1, and then sine of whatever that theta is going to equal, now it's the right side, so it's the bottom n, which is 1.33, and the sine of whatever that theta is. Now that we kind of understand how refraction works, let's try solving some practice problems. I'm getting these from page 354 and number 1. Okay, so it wants to know the refracted angle when light enters glass from the air, long story short. So let's draw this out. So here's your normal, and here's your beam of light at angle theta, which they said is 45 degrees. So we know light is going to get bent towards the normal, and we're solving for the angle of refraction. So we're going to use Snell's law. Again, n1 is coming from the air, so we use 1. And the angle of incidence in the air is 45 degrees, so that's what we use. And all that equals n2, which is the index of refraction for glass, 1.5 times sine of theta, which is the angle of refraction and what we're solving for. So to start this off, we're just going to see what 1 times sine of 45 is, which looks like 0.707. We're going to divide that by 1.5 to get 0.47 equal to sine of theta. Now we're going to have to get theta out of that sine, so we're going to have to use arcsine. If you're not familiar with arcsine, it's the little sign with a little -1 exponent on your calculator. You can access it by pressing second sign. So we need to do that to both sides. So theta is going to equal arcsine of 0.47, and that gives us 28.1 degrees. Alright, so here's another slightly harder practice problem that comes from page 364 in your book, problem number 9. So essentially what we have is light going from water into glass, and they want the angle of refraction. So we set this one up just the same as the other one using Snell's law. The n value for water is 1.33 and glass is 1.5. So let's draw the light being refracted here. So let's just write out Snell's law here, making sure we attach the right values to each variable. Plug and chug. And take the arcsine of 0.25 over 1.5, and that gets you 20.4 degrees. Now we don't just have to solve for the angle of refraction, we can also solve for the n value if needed. So let's take problem number 3 here. They give you both the angle of incidence and the angle of refraction, and they want you to solve for the n value of quartz. So we're just going to draw our angle of incidence here, which is 30 degrees, and draw our angle of refraction, which is 20 degrees. Again, assuming this comes from air, we write out Snell's law, but this time we're given the angle of refraction, which is said to be 20 degrees, and we need to solve for n. So it's not too bad, just make sure you put everything in your calculator correctly. You should get an n value of around 1.46. And remember, there's no units on the index of refraction. Alright, so another concept you need to understand is the concept of the critical angle. Now this will only happen when the light is going from a high index of refraction, or a high n value, to a low index of refraction, or low n value. To explain why this only works from high to low is because when we're going from low to high, like in all of our practice problems, if you remember, the light was bent towards the normal. Now that it's reversed, the light will be bent away from the normal. So let's just draw our light here coming from a low n value to a high n value. The critical angle is the angle at which the light must strike the boundary to produce a refracted angle of 90 degrees, which looks just like this, laying flat along the x-axis. So if this is water and air, what would be the critical angle? We're still going to have to set this up using Snell's law. We're just going to assume that the refracted angle is 90 degrees, and we're going to solve for the critical angle. That's important to understand, that the critical angle is not 90 degrees. It's the angle of incidence that causes the refracted angle to be 90 degrees. So set this up like normal using 1.33 for the end value of water, and we're solving for the critical angle, so that gets attached to the water side of the equation. And like I said, assume that the refracted angle is automatically 90 degrees. So sine of 90 is 1, and we'll divide that by 1.33 to get 0.75. And we'll take the arc sine of that. So put it into our calculators, and it looks like 48.6 degrees is the critical angle. Okay, the last thing you need to know is what fiber optics are and how they work. Basically, they deal with the principle of total internal reflection, which means that the angle of incidence is greater than the critical angle, causing the refracted angle to be reflected. So let's see what that looks like. Okay, so fiber optics are usually just a dense tube like this. And let's just say it's a material like plastic. So when light enters the tube, it hits the side, and because the material is so dense and the angle is so great, it gets reflected and stays inside the tube. The light is constantly bouncing around inside the tube because it can't escape. So this happens over and over again millions of times inside the tube. And this is just me being an idiot overcomplicating things. So fiber optics is what Brandon showed you in class with that spiral thing and the laser pointer. The thing you should take away from fiber optics is that you can bend it in any position and the light will always carry through. So that's why it's in a giant spiral and it can come out the end, is because it can't escape, so it has nowhere to go but the end. Fiber optics practical applications are used in telephone wires for sending signals, since they can go across millions of miles of land and they can be bent and twisted and curved around streets. Alright, so what I have here is a fiber optic sphere, and basically it's the same principle, total internal reflection, but it's just kind of cool to look at. I think it's just a cool marble or something like that. But if we take a light source, I'm using my watch, and we shine it through there, we can see that it carries straight through the ball, but as soon as we turn it, we hit the critical angle and we can't see the light anymore. So that's why you can see it when it's straight on, but when you turn it, you can't see it anymore because it's total internal reflection. So I don't know.